Welcome back. This is Fundamentals of Micro and Nano Fabrication. I am Sushobhan Awasthi from IC Bangalore, and today we are going to talk about additive manufacturing. Specifically, how do we add things on top of a substrate to do microfabrication. But before that, we will take a quick detour. I want to give a little primer on defects, because in order to understand some of the things that I am going to talk about, I will be using terminology that a lot of you may not know. So, if you look at defects in a semiconductor, they can be categorized in several different ways. This is just one of the categorizations that I have picked up. You can categorize them on the basis of dimensionality. So, for example, you can have a defect that is 0 dimensional, which is that say an atom is missing or an extra atom is present, etc. It can be 1 dimensional, where a chain of atoms or a string of atoms is missing, or there is an added string of atoms. So, those are things like dislocation, disclinations, etc. Some of the defects are 2D. You can imagine surface, right. So, surface there is a break in the lattice symmetry, so that would cause defects. And there are other defects which are 3 dimensional. You can have a precipitate inside your semiconductor, which can be a defect. You can have voids, cracks, etc. Now, even though I have tried to argue that a substrate does not have defects, or we try very hard to make substrates which do not have defects, fact of the matter is there is always going to be some amount of defects, and the performance of a device is extremely sensitive to these defects. So, removal of these defects, and in order to do that, to understand how these defects form, is very important. So, let us talk with some 0D defects, specifically vacancy and impurities. So, what do I mean by that? Supposing you take a lattice, say this blue atoms represent silicon and they exist in a 2D lattice. Every now and then you might encounter an impurity, so which is not silicon, which is some alien atom, but that is not sitting at the lattice site, but somewhere in the middle. Such are called interstitial impurities. Okay. Let me get my pointer here. Yeah. So, those are called interstitial impurities. Sometimes the impurities are not in the interstitial site, but actually are sitting at a lattice site. So, instead of silicon, you have the impurity atom sitting. So, those could be, for example, this green, which is called a substitutional impurity. Sometimes you can have the silicon atom itself not sitting at its lattice site, but sitting somewhere in the middle. Those are called self interstitials. Sometimes you can have a silicon atom missing at a lattice site, so that would be a vacancy. So, there are essentially these 4 types, right. So, depending upon whether it is interstitial or substitutional, or whether it is self, you can have a vacancy or a interstitial. Each of these impurities cause something inside the crystal. You can imagine that if this because of interstitial impurity, you would have a tensile stress, compressive stress, depending upon whether this atom is small or not. If you have a substitutional impurity, it can cause tensile or compressive stress depending upon the size. So, if the size is larger than the silicon atom, it might cause a compressive stress. If the size is smaller than the silicon atom, it might cause a tensile stress. Self-interstitial, because they are the same size, tend to always call the compressive stress, and vacancies tend to call the tensile stress. So, the stress in a film also changes the impurity, also changes with the impurity dynamics of the material. In fact, this is one of the ways in which people who do film growth often control the properties of films. Things become more interesting in alloys, because in alloys you do not have just one type of atom, you have maybe 2 or more. So, and then in those cases things are a little different. Here is an example. Supposing you have a germanium silicon alloy, silicon-germanium alloy. Now, that is a substitutional solid where the germanium actually sits where silicon is supposed to sit. Such alloys can lead to doping, right. So, we discussed the concept of doping in the very first lecture, and there we sort of looked at that how if you substitute a group 5 element into silicon, you can actually cause n-type doping. Now, for that to occur, the group 5 element must be in the position where silicon is supposed to be, only then the bonding occurs and you get that extra electron, right. If on the other hand, that alloy forms an interstitial solution, where instead of being at the lattice position, it is somewhere in the middle of the lattice. In this case, you have an interstitial solid solution. A classic example of this is carbon inside silicon. In general, such materials do not cause doping, because the bonding does not occur, and if there is no bonding, there is no extra electron. So, carbon is not a dopant inside silicon. The third thing that can occur is that the second material precipitates inside the primary material. Of course, in silicon, and this can happen often when you have oxygen precipitates inside silicon under certain extreme conditions. These can often cause 3D defects, because what they do is they disrupt the lattice structure and of the whole crystal. Here is an example of silicon dioxide precipitate inside silicon, where there is a 3D defect formed because oxide has precipitated inside the silicon lattice. Right. If you have ionic crystals which have both cation and anion, so this is not a completely covalent bond but slightly ionic bond, then there are another type of defect that can form. These are called the Schottky and the Frenkel defects. In the Schottky defect, there is a pair, cation and anion both are misplaced. So, supposing you take say sodium chloride, both sodium one sodium cation is missing and one chlorine anion is missing. When this happens, of course, this crystal on its own remains neutral, there is no effect, but you do have now two vacancies, right, one because of the anion and one because of the cation. This typically happens for solids where both cation and anion are small or of the same size. If on the other hand you go to a material where the cation and anion have different size, the cation tends to be much smaller than the anion and tends to move around more or become interstitial more. So, in that case you have a system where even though the whole solid remains neutral, one of the cations, which is this red thing, has popped out of its lattice position and has started roaming around. Such are called Frenkel defects. These are often happen when the ionic solid has a very large anion, for example silver iodide, and the cation is very small. Now, you would think that a perfect material, there should be a concept of a perfect material which does not have any vacancy or interstitials, right, at least no self interstitials and so self vacancies. It turns out thermodynamics predicts that that cannot happen. Because of entropic reasons, you always will have certain vacancies and interstitials. Here is a very basic understanding of why. So, supposing you take a material, and you can take two cases when there is the perfect semiconductor. Now, this is the happiest state, so that it is the lowest energy state, and now you create a vacancy inside this material. So, to do that, you have to break some bonds, you have to pay some energy price. So, that is your enthalpy. This is the enthalpy you have to pay to create that vacancy. Now, this would mean that ideally speaking, we should never be doing this. The system would always like to remain low energy state, but that is only looking at enthalpy. In reality, system tries to also reduce entropy. So, the reason what actually happens is you try to reduce the free energy, and the free energy is a sum of enthalpy and also conformational entropy. So, if you want to reduce both of them, then there is a certain minimum number of vacancies or a certain amount of disorder that the crystal will try to accumulate such that its free energy is the lowest. And you can do some basic calculations to show that that concentration of equilibrium defects or equilibrium vacancy interstitials is given by its enthalpy and by this formula. So, two things to note here. First, n is exponentially increases with temperature. So, at higher temperature you have much higher concentrations of vacancies and interstitials. This is an important point. We shall use this later when we look at diffusion. So, at high temperature you will fundamentally create more defects. Okay. System has more energy to move around, and that will cause more defects. Here is a very interesting example. I would never quiz you on it, but it is a very interesting side reading. I urge you to go and look at this paper that was published in Nature some time back, where they actually were able to take a video where the vacancy interstitials were getting created and destroyed with time. They also in fact have a very interesting movie where you can physically see the vacancies interstitial get created and destroyed. I will not explain this anymore, urge you to go and look at the video. With that, let me move to some 1D defects. So, the most common ones are dislocations. So, there are two types of dislocations. Let us first talk about edge dislocations. The edge dislocation is if you take an perfect crystal and then you create some shear stress such that one plane is moving in the left hand side and one plane moving to the right hand side, and when you do that, it jumps by one lattice position. So, what if you look at the cross section, this is what you will see. So, you had a perfect crystal, but then you tried to create some stress and it shifted, but it did not completely shift. So, these bonds remained, but this bond got broken. What that means is now you have an extra plane of atoms in the middle, right. So, that is the visualizations, that you have an extra plane of atoms somewhere in the middle, and that is what is giving you this 1D defect. This can also happen in a screw dislocation where there is certain rotational component to it. Often these things are expressed in Burger's vector. So, yeah, the screw dislocation is associated with the Burger's vector. Details are not sort of important. The point is to remember that you can have these sorts of defects inside a material, and when you are doing crystal growth or when you are doing thin film deposition, you will have these problems. So, here is an example of what dislocation, for example, looks like inside a strontium titanate crystal. This is the TM image, this is the simulation, and you can actually see that the two match exactly, right. So, you can actually see that there is an extra layer of atoms here. You can also have grain boundaries. Even though in a silicon we try to make single crystalline, but I also explained to you that you do have something called multi-crystalline silicon where you do not have a single grain. So, in those cases, if you zoom in enough, you will get to a point where there is one grain on and one orientation on the left hand side and one grain and one orientation on the right hand side, and in the middle there is a grain boundary. So, this is what the grain boundary typically looks like. It essentially just has two different crystal structures on the left and right. Sometimes the grain boundaries are very high angle grain boundaries, which tend to be worse. Sometimes the grain boundaries have low angles, which tend to be slightly better in terms of defects. Certain defects can also occur at the surface, because if you think about it, surface is an extreme case of a grain boundary, because the surface there is only materials only on one side, on the other side it's either a different material with a different crystal structure or an amorphous material or air, right. So, here is an example where you take crystalline silicon, you deposit silicon nitride, which is amorphous. This is amorphous, this is crystalline. So, somewhere in the middle must be an interface where silicon ends, and that silicon that plane of silicon atoms does not have satisfied valencies. They are not bonded to anything, or they are not perfectly bonded to anything, and that means there is a certain density of defects at that interface. So, that was a quick primer on defects. We will be using some of this terminology as we go along. You do not have to focus on the details of these types of defects, that would be part of a materials course, but you should be aware when I say that this process creates dislocations, what dislocation means. So, with that, thank you for listening, and next we will talk about diffusion.